Hello everyone. In this video I'm going to review how to solve a quadratic equation, or excuse me, a trigonometric equation that requires the use of factoring or substitution, in particular as it relates to quadratic functions. So I'm solving cosine of 2 theta plus 3 equals 5 of cosine theta, or 5 times cosine theta, for the interval 0 to 2 pi. One of the things we want to remember with problems such as this is it's usually easier if both of our trig functions are the same, and in this case they're both cosine, which is good, but also that we have cosine, or whatever the trig value is, of just theta. In other words, we don't want a modified argument, or in this case we don't want to have the 2 theta. That makes it difficult. When we solve problems like this, having both cosine of theta in each spot allows us to use more factoring rules. So I'm going to use one of my identities. I want to find an appropriate identity that brings cosine of 2 theta into where I have a cosine of just theta. And using one of my double angle theorems, or substitutions, I know that cosine of 2 theta is equal to 2 cosine squared of theta minus 1. So again, this was the equivalent of cosine of 2 theta, one of my identity rules. Now I still have plus 3 equals 5 cosine of theta. Now I have, in all cases, the same trig function and the same argument, in this case just theta. Now it would help to combine any like terms, which in this case is going to be my negative 1 and 3 to give me 2. And I also want to get all my terms on one side. So that means I'm going to move my 5 cosine of theta by subtracting it as a whole to each side. So it leaves me with 2 cosine squared of theta minus 5 cosine of theta plus 2 equals 0. Now that I have the same trig function, I can look at this in the same way I would look at a quadratic function. Thinking of it that way may make it easier to understand how we can solve this, because having the cosine is kind of cumbersome. If I were to substitute and instead say, I'll call it x is equal to cosine of theta, this is equivalent to 2x squared minus 5x plus 2 equals 0. Now I can solve this as I would any quadratic function, or any quadratic equation. I could use factoring, completing the square, the quadratic formula. Usually factoring is easiest, as long as we can. In this case, we certainly can. If we were to factor each of these, we'd have 2x minus 1 and x minus 2 equals 0. So, resubstituting again, this is now 2 cosine of theta minus 1 equals 0, and cosine of theta minus 2 equals 0. Now when I solve each one of these, on my left side, I'll add 1 and then divide by 2. And now I'm left with cosine of theta equals 1/2. Here I'll add 2 to each side. I'm left with cosine of theta equals 2. Similar to other trig equations, from here I want to identify what angle or what radian measure gives me 1/2. So I need to refer to my 30, 60, 90 or 45, 45 right triangles. In this case, the 30, 60, 90 will give me a 1/2. And since I'm talking about cosine, the adjacent over hypotenuse, I want to use 60 degrees or pi over 3. Now, of course, I need to consider what quadrant I'm in. Since cosine is positive, that confines me to quadrants 1 and quadrants 4. So I have pi over 3 in quadrant 1. In quadrant 4, using pi over 3 as a reference angle, my other angle will be 5 pi over 3. And that's within one full revolution, from 0 to 2 pi, so I'm good. My second equation, cosine is equal to 2. Now that seems a little strange, it's because that falls outside of our normal range. If you recall, for the cosine graph, the range is from, of your general cosine graph, is from 1 to -1. And we assume nothing's been modified, so that means that answer of 2 falls outside of the range, which means that this is an impossibility. We can't do anything with it. So we just ignore it. We consider that part of it to have no solution. Overall, though, we do have solutions for cosine of theta equals 1/2. Those are pi over 3 and 5 pi over 3, so those become our final answer.